Hello there, and welcome back to the Science Sleepy Minds. Tonight, you are lying on your back in an open field somewhere far from the city. The grass beneath you is cool and slightly damp, and the sky above is doing that thing it does when there are no streetlights for miles. It is showing off. Thousands of stars, millions maybe. A faint ribbon of the Milky Way draped across the darkness, like someone spilled powdered sugar across black velvet. It is beautiful. It is ancient. And every single point of light up there is keeping a secret from you. Because between those stars, between the galaxies, between the atoms that make up your own hand resting on your chest right now, there is an almost incomprehensible amount of nothing, and that nothing might be the most terrifying thing in the entire cosmos. Tonight we're going to talk about why the universe is so absurdly, overwhelmingly empty, and why that emptiness might not be an accident. Fair warning, you probably will not survive this one emotionally intact. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop a comment telling me where you're listening from and what time it is where you are. I always love reading those. Someone is always tuning in at 3 in the morning from somewhere unexpected, and honestly, that is my favourite thing. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You keep staring at that sky. You let your breathing slow down, and you start to think about something that most people never really sit with long enough to feel uncomfortable. You think about how far away everything is, not in the vague, poetic sense you learned in school, but in the raw, mathematical, almost offensive sense. The nearest star to our Sun, Proxima Centauri, is about 4.25 light years away. That sounds manageable until you remember that a single light year is roughly 9.5 trillion kilometers. So the nearest star, the closest possible neighbour in our little suburban corner of the Milky Way, is sitting about 40 trillion kilometres from you right now. If you could somehow board the fastest spacecraft humanity has ever built, the Parker Solar Probe, which screams along at around 690,000 kilometres per hour, it would still take you more than 6,000 years to get there. 6,000 years. That is roughly the entire span of recorded human civilization, from the first Sumerian cuneiform tablets to the phone you might be holding right now. All of that history, all of those empires and plagues and love letters and terrible haircuts, compressed into a single one-way trip to the nearest front porch. And that is just the beginning of the emptiness. You pull back a little further in your mind, you zoom out. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. Scientists still argue whether the true count leans toward the conservative or extravagant end. But let us be generous and say there are a lot of stars. Now here is the thing nobody tells you at planetarium shows. Those stars are ludicrously far apart from each other. The average distance between stars in our galaxy is about 5 light years. That means if you shrank the sun down to the size of a grain of sand, the nearest grain of sand would still be several kilometers away. The galaxy, for all its grandeur, is almost entirely vacuum, almost entirely nothing, and that nothingness scales up in ways that start to feel personally offensive. The Milky Way itself is about 100,000 light years across, which is impressive until you learn that the nearest major galaxy, Andromeda, is 2.5 million light-years away. The space between galaxies dwarfs the galaxies themselves the way an ocean dwarfs a single fish, and between galaxy clusters there are voids, genuine, colossal regions of space where there is essentially nothing at all. No stars, no gas clouds, no rogue planets, just darkness stretching for hundreds of millions of light-years in every direction. There is a quirky little detail that captures this beautifully. If you picked a random spot in the observable universe, truly random, like throwing a cosmic dart, there is about a 99.9999 something percent chance you would land in a place where the nearest atom is further away than you could ever travel. The universe, at its core, is not a place full of things. It is a place full of distance. And you are lying in that field, and you are starting to feel it. Not just intellectually, but somewhere deeper. Somewhere in the part of your brain that evolved to feel small when it looked up at the night sky. Back in 1995, the Hubble Space Telescope pointed at a tiny patch of sky that appeared completely empty to ground-based telescopes, a patch no bigger than a grain of sand held at arm's length. They kept the shutter open for 10 consecutive days. When the image came back, that blank little patch contained over 3,000 galaxies, each one home to billions of stars, each one impossibly far from the next. The photograph, known as the Hubble Deep Field, became one of the most important images in the history of science, not because it showed us how full the universe is, but because it showed us how full it is and how quiet it remains. That quiet is the part that should make the hair on the back of your neck stand up. Because with that many galaxies, that many stars, that many potential planets, and we now know planets are extraordinarily common, nearly every star has at least one. The universe should be noisy, it should be bustling, it should be absolutely crawling with civilizations building things, broadcasting signals, lighting up the darkness with the unmistakable fingerprints of technology. And yet, when you point your most sensitive radio telescopes at the sky, when you scan for laser pulses or infrared waste heat, or any other conceivable signature of intelligence, you get the same answer every single time. Silence, nothing. A void not just of matter but of meaning. And as you lie there in that damp grass listening to the crickets and your own steady heartbeat, a question starts to form in the back of your mind. A question that a physicist once asked over lunch and accidentally changed the course of human thought forever. Where is everybody? You let that question settle into the grass beside you, and you decide to do something reckless. You decide to actually grasp how empty this place really is. Not just the space between stars, not just the gaps between galaxies, but the emptiness woven into the fabric of reality itself. Because the nothing is not just out there. It is in here. It is in you. Start with your own hand. You lift it up against the starfield and spread your fingers. That hand looks solid. It feels solid. You can knock on things with it, and they make a satisfying sound. But if you could somehow zoom in past the skin cells, past the molecules, past the atoms themselves, you would find something disturbing. An atom, the basic building block of everything you have ever touched or tasted or loved, is almost entirely empty space. The nucleus at the centre, where nearly all the mass lives, is absurdly small compared to the atom as a whole. If you blew an atom up to the size of a football stadium, the nucleus would be a single blueberry sitting on the 50-yard line. The electrons would be somewhere up in the nosebleed seats, and everything in between, every row, every hot dog stand, every overpriced parking space, would be nothing, just void. Physicists still debate whether those electrons are even things in the traditional sense or probability smears, haunting the space around the nucleus like tiny existential crises. Either way, you are made of emptiness pretending to be solid, which is exactly the kind of revelation that hits differently at 2 a.m. Now scale that up. Your entire body contains roughly 7 octillion atoms. That is a 7 followed by 27 zeros, which is a number so large it has essentially quit trying to mean anything. And every single one of those atoms is running the same scam, a tiny knot of mass surrounded by a vast personal void. If you could somehow squeeze out all the empty space inside every atom in your body, compress yourself down to just the nuclear material, you would fit into a cube smaller than a grain of dust. The entire human race all 8 billion of us crushed to our essential matter would fit into a space roughly the size of a sugar cube. And yet here we are, taking up seats on buses and arguing about parking spaces, all because the electromagnetic force is politely maintaining the illusion that we are solid objects. This emptiness is not a flaw in the design. It is the design, and it replicates at every scale you care to examine. You pull your attention back to the solar system. You grew up with those classroom models, the ones where the planets are colourful balls hanging from a wire, spaced a few inches apart, orbiting a grapefruit-sized sun. Those models are lies, beautifully painted educational lies. In reality, if you shrank the sun down to the size of a basketball, the Earth would be a small peppercorn sitting about 26 meters away. Jupiter would be a walnut roughly 140 meters out, and Neptune, poor frozen Neptune, would be a slightly smaller walnut sitting nearly a full kilometre from that basketball. Everything in between is emptiness. If you have ever driven through West Texas or the Australian outback and felt that eerie sense of flatness and absence stretching in every direction, congratulations! You have experienced a pale, human-scaled echo of what the solar system actually feels like. And the solar system is cozy compared to what comes next. You zoom out further. You're now hovering above the Milky Way, looking down at a pinwheel of light roughly 100,000 light-years from edge to edge and about 2,000 light-years thick. It contains all those hundreds of billions of stars. But here is the thing that makes your stomach drop. Even within this galaxy, space is overwhelmingly winning. Stars occupy such a tiny fraction of the galactic volume that if two galaxies were to collide, and they do, the Milky Way and Andromeda are on a collision course right now, due to merge in about 4.5 billion years. The odds of any two stars actually hitting each other are essentially zero. The galaxies will pass through each other like two swarms of bees in a cathedral. That is how much nothing there is even inside a galaxy. Now step outside the galaxy. You enter intergalactic space, and the emptiness becomes almost philosophical. The average density of the universe is roughly 5 atoms per cubic meter. 5. You could scoop up a cubic meter of space, and most of the time come back with a handful of hydrogen atoms and a growing sense of futility. There is a wonderfully strange fact that captures this. The densest thing most people will ever encounter is osmium, a metallic element that packs about 43,000 kilograms into a single cubic meter. The universe, on average, packs about 1/trillionth of a kilogram into that same space. The contrast is so extreme, it almost sounds like a joke the cosmos is playing on itself. And then there are the voids, not the casual, conversational emptiness between galaxies, but the true voids, the supervoids. These are regions of space where even the thin scattering of galaxies found elsewhere simply stops. The Bhuta's void, discovered in 1981, is roughly 330 million light-years across and contains almost nothing. When astronomer Greg Aldring described it, he said that if the Milky Way had been placed at the centre of the Bhut's void, we would not have known other galaxies existed until the 1960s. Let that sink in. Our entire understanding of the cosmos, the entire history of extragalactic astronomy, would have been delayed by decades simply because of where we happen to sit. The void is so empty that its existence was initially met with disbelief. Some researchers suggested it had to be an observational error. It was not. You're starting to sense a pattern now. At every level, atomic, planetary, stellar, galactic, cosmic, the dominant feature of reality is absence. The stuff, the matter, the things you can name and touch and orbit are the exception. They are the rounding error. The universe did not build itself around matter. It built itself around the space between matter. And as you lie in that field, feeling the slow rotation of the Earth beneath your back, you begin to wonder if all that emptiness is trying to tell you something. because emptiness on this scale does not feel accidental. It feels architectural. That architectural feeling stays with you as the night deepens, and your mind drifts to a summer day in 1950. Not your summer day, obviously. This one belongs to a group of physicists walking to lunch at Los Alamos National Laboratory in New Mexico. The desert heat is doing its thing. The conversation is loose, playful, the way it gets when very smart people are temporarily freed from the burden of building things that could end the world. Someone brings up a recent New Yorker cartoon about aliens stealing public trash cans, and the group has a good laugh. Flying saucers are in the news that year. The topic is light. The mood is easy. And then one of the men, a short, cheerful Italian-American with a reputation for being the fastest mental calculator in any room he entered, sits down at the lunch table, looks around at his colleagues, and says something that lands like a brick wrapped in velvet. Where is everybody? The man is Enrico Fermi. He has already won a Nobel Prize by this point. He built the first nuclear reactor under the bleachers of a squash court in Chicago, which is the kind of sentence that sounds made up but is annoyingly true. He is known for his ability to estimate almost anything from first principles: how many piano tuners are in Chicago, how far a nuclear blast will carry, whether the atmosphere will ignite during a bomb test. That last one he actually had to calculate in advance, and he got the comforting answer of probably not, which is the most unsettling use of the word probably in human history. So when Fermi asks a question, people listen. And when he asks this particular question, the table goes quiet. Because the math is simple and the answer should be obvious. The Milky Way is old. Staggeringly old. It started forming roughly 13 billion years ago, only a few 100 million years after the Big Bang itself. Stars have been burning in it for almost that entire span. The Sun and Earth are only about 4.5 billion years old, which means there were stars in this galaxy burning for 8 or 9 billion years before our solar system even existed. If even one civilization somewhere in the Milky Way developed interstellar travel, not warp drives or wormholes, just slow, patient, generation ship-style colonization, it could theoretically spread across the entire galaxy in a surprisingly short time. Estimates vary, and scholars still argue whether the number is closer to 1 million or 100 million years, but even the most conservative figure is a blink compared to the age of the galaxy. A single ambitious species starting 1 billion years before us could have colonized every habitable world in the Milky Way and still had time to get bored and take up pottery. And yet when we look at the sky there are no signs of them, no megastructures blocking starlight, no radio signals, no probes orbiting our sun, no ancient artifacts buried in lunar dust, nothing. Fermi did not write a paper about this. He did not even seem to think it was that big a deal at the time. The conversation moved on, but the question burrowed into the minds of the people at that table like a splinter, and over the following decades, it grew into one of the most persistent and unsettling problems in all of science. It became known as the Fermi paradox, though some historians prefer to call it the Fermi question, since the paradox label was applied later by others who felt the weight of it more heavily than Fermi apparently did. There is a quirky footnote to the whole affair. No one is entirely sure who else was at the lunch table that day. The names Edward Teller, Herbert York and Emil Konopinski are usually cited, but the accounts differ slightly depending on who is telling the story, and none of them wrote it down at the time. The most detailed recollection came from York, years later, and even he admitted his memory was fuzzy. So the most famous question in astrobiology was born at a lunch that nobody properly documented. Science, everyone. You're still lying in that field and now the stars look different. A minute ago they were beautiful. Now they are suspicious. Because Fermi's question is not a cute philosophical riddle. It is a statistical emergency. Our galaxy alone contains somewhere between 100 billion and 400 billion stars. Current estimates, informed by data from NASA's Kepler Space Telescope, suggest that roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. The not too hot, not too cold orbital sweet spot where liquid water can exist. That gives you billions of potentially habitable worlds in this galaxy alone. Billions. And the observable universe contains at least 2 trillion galaxies. The number of potential homes for life is so large that writing it out would take longer than the life you are currently living. So you run the thought experiment the way Fermi would have. You assume that life is rare. Fine. You assume that intelligent life is extremely rare. Sure. You assume that technological civilizations are so improbable that they arise on only 1 in a billion habitable planets. That still gives you thousands of civilizations in the Milky Way alone, and trillions across the observable universe. You can make the assumptions as pessimistic as you like, crank every dial toward nearly impossible, and the numbers still spit out a universe that should be noisy, crowded, messy with the evidence of intelligence, and yet silence. The stars burn on, indifferent. The crickets near your feet do not care about statistical paradoxes. A satellite slides across the sky, steady and unhurried, and for a moment you wonder if something out there is watching it the way you watch an ant cross a sidewalk. Curious, briefly, before moving on. Fermi's question is really 2 questions wearing a trench coat. The first is scientific. Given the size and age of the universe, why have we found no evidence of extraterrestrial intelligence? The second is existential, and it is the one that keeps physicists awake at night and makes cosmologists quietly change the subject at dinner parties. If we are alone, why? And if we are not alone, where is everybody hiding, and what are they hiding from? The night suddenly feels a little less peaceful. The emptiness between those stars is no longer just distance. It is starting to look like evidence. The evidence keeps piling up in your mind as a cool breeze moves across the field. You pull your jacket a little tighter and think about a man standing in front of a chalkboard in 1961 writing down an equation that looks deceptively simple. His name is Frank Drake. He is an astronomer at the National Radio Astronomy Observatory in Green Bank, West Virginia, and he is about to do something either very brilliant or very foolish. He's going to try to calculate the number of detectable civilizations in the Milky Way using nothing but a string of multiplied probabilities. The equation he writes will eventually bear his name, and it will become the most famous formula in astrobiology. Not because it gives a definitive answer, but because it reveals, with almost painful clarity, how much we do not know. The Drake equation looks like this in plain language. You take the rate of star formation in the galaxy. You multiply it by the fraction of those stars that have planets. You multiply that by the number of planets per star that could potentially support life. Then you multiply by the fraction of those planets where life actually develops. Then by the fraction where intelligent life evolves. Then by the fraction that develops technology capable of releasing detectable signals into space. And finally, you multiply by the length of time such civilization broadcast those signals before they go silent, whether through self-destruction, boredom, or something worse. Drake did not pull this equation out of thin air at his kitchen table. He designed it as a framework for a small scientific meeting he was organizing. The first ever gathering dedicated to the search for extraterrestrial intelligence. The meeting had exactly 10 attendees, which is a wonderfully humble beginning for a field that now involves billion-dollar telescopes and has its own acronym. SETI, they would call it. Search for Extraterrestrial Intelligence. At that 1961 meeting, Drake and his colleagues plugged in their best guesses for each variable, and arrived at an estimate of roughly 10 communicative civilizations in the galaxy at any given time. 10, in a galaxy of hundreds of billions of stars. It was a small number, but it was not 0. and that was enough to justify pointing radio dishes at the sky and listening. The trouble with the Drake equation, as you're probably sensing, is that most of its variables are educated guesses stacked on top of other educated guesses, balanced on a foundation of wishful thinking. In 1961, we did not even know for certain that other stars had planets. That particular variable was pure speculation. It was not until 1992 that the first exoplanets were confirmed, orbiting a pulsar, of all things, which is the cosmic equivalent of finding an apartment above a nightclub that plays nothing but radiation. The first exoplanet around a sun-like star, 51 Pegasi b, was not discovered until 1995, and the floodgates truly opened with the Kepler Space Telescope, launched in 2009, which found thousands of exoplanets and revealed that planets are not rare cosmic accidents, but standard equipment for stars. Almost every star you see has at least one world circling it. Many have several. So that first variable, the fraction of stars with planets, went from uncertain to essentially 1. Planets are everywhere, and the habitable zone planets, the ones sitting at the right distance for liquid water, turned out to be shockingly common as well. Kepler data suggests there could be as many as 40 billion Earth-sized planets in habitable zones in the Milky Way alone. 40 billion chances, and that is just in one galaxy out of 2 trillion. You would think this news would have made Drake's equation sing. More planets should mean more life, which should mean more civilizations, which should mean more signals. But here is where the math starts to feel like a horror story. Because as the early variables in the equation got pinned down with real data, and they mostly pointed toward abundance, the silence of the universe did not break. No signals arrived, no megastructures appeared, the radio telescopes kept listening and the sky kept saying nothing, which means, logically, that one or more of the later variables in the equation must be brutally, catastrophically small. The fraction of habitable planets where life actually starts? We do not know. We have a sample size of exactly 1, which is the worst possible sample size for drawing conclusions about anything. Life appeared on Earth remarkably quickly, possibly within the first few 100 million years, which some scientists take as evidence that abiogenesis is easy. Others counter that this could be survivorship bias, since we could only exist on a planet where life did start, so of course it looks easy from our perspective. Scholars still argue whether the origin of life is a chemical inevitability that happens on nearly every wet rock, or a cosmic fluke so improbable it has only occurred once in the entire observable universe. The gap between those two positions is not a crack, it is a canyon, and the variables only get murkier from there. What fraction of planets with life develop intelligent life? On Earth, life existed for roughly 3.5 billion years before anything resembling complex intelligence showed up. Bacteria had the planet to themselves for an almost embarrassingly long time. Dinosaurs ruled for 165 million years and never once invented radio. Intelligence, at least the technological kind, might be evolution's rarest accident, a fluke of primate social structures, opposable thumbs, and whatever strange pressure made our ancestors' brains triple in size over 2 million years in what anthropologists sometimes call the most rapid encephalization event in the fossil record. There is a fringe but persistent idea that intelligence of our type is actually maladaptive in the long run, that it inevitably leads to self-destruction, which would make the Drake equation's final variable, the longevity of a broadcasting civilization, tragically small. Drake himself lived to see the equation evolve far beyond his original napkin math exercise. He passed away in 2022 at the age of 92, having spent a lifetime listening to a universe that never called back. And as you lie in your field, watching those 40 billion potential homes twinkle overhead in this galaxy alone, you start to understand why the silence is not just disappointing. It is diagnostic. Something in that equation is broken. Something is killing the math. And the next question, the one that makes cosmologists pour a second drink, is figuring out which variable is the murderer. The murderer has a name, and it sounds like something out of a particularly grim philosophy seminar. It is called the Great Filter, and once you understand it, you will never look at the night sky the same way again. You're still in that field, but the stars have stopped feeling like decorations. They're starting to feel like crime scenes. The concept comes from an economist, which should tell you something about how far this question has reached beyond astronomy. In 1996, Robin Hanson, then at George Mason University, published a paper that tried to explain the Fermi paradox by proposing that somewhere in the long chain of events between dead chemistry and galaxy-spanning civilization, there exists at least one step that is almost impossibly hard to pass, a bottleneck so severe that virtually no species in the history of the universe has ever made it through. He called it the Great Filter, and the name stuck because it is exactly as ominous as it sounds. Think of it like this. You're standing at the bottom of a staircase. Each step represents a major transition in the development of a technological civilization. Step 1. A planet forms in the habitable zone of a stable star. Step 2. Basic organic chemistry produces self-replicating molecules. Step 3. Simple single-celled life appears. Step 4. Complex cells with nuclei develop. Step 5. Multicellular life emerges. Step 6. Intelligent beings evolve. Step 7. Those beings develop technology. Step 8. The technology allows them to colonize other worlds. Step 9. They expand across the galaxy. Somewhere on this staircase, there's a step that is not just hard, but functionally impossible for almost everyone who attempts it. The Great Filter is the step where nearly every aspiring civilization trips and falls and never gets up. The question that Hansen posed, and that has haunted astrobiologists ever since, is devastatingly simple. Which step is the filter? Because the answer to that question determines whether humanity's story is miraculous or doomed. If the Great Filter is behind us, if it is one of the early steps, like the origin of life itself, or the jump from simple to complex cells, then we have already passed the hardest part. We are the lucky ones who made it through. The universe is empty because almost nobody else managed to get this far, and we're sitting on the other side of the bottleneck, bruised but alive, looking back at a staircase littered with the remains of 1 trillion failed experiments. In this scenario, the silence is a testament to our absurd good fortune. We are the winners of a cosmic lottery so improbable that we cannot even calculate the odds properly. But if the Great Filter is ahead of us, if the really hard step is something that happens after a civilization reaches our level of development, then the silence is not a trophy, it is a warning. It means that countless civilizations before us reached exactly this point. They looked up at the same stars, they built their own radio telescopes. They probably even had their own version of this exact conversation, lying in their own fields on their own planets, wondering where everybody was. And then something happened to them. Something they did not see coming, or something they saw coming and could not stop. Something that filtered them out of existence with such thoroughness that not a single trace of their technology, their art, their desperate final broadcast survived long enough for us to detect. The Great Filter is essentially the universe's way of running a quality control check on civilizations, and the rejection rate appears to be approximately 100%. Hansen's original paper laid out the logic with the cold precision you would expect from an economist. He noted that the more steps in the chain that turn out to be easy, the more likely it is that the filter is still ahead. Every time scientists discover that a particular transition, say, the formation of habitable planets, is common, it sounds like good news. But in the context of the Great Filter, common early steps are actually terrifying. Because if all the early steps are easy and the universe is still empty, then the hard part must be something that happens later. Something that happens to civilizations that have already figured out fire and physics and nuclear energy and are standing right about where we are standing now. There is a quirky historical footnote here that captures the dread perfectly. In 2004, the philosopher Nick Bostrom wrote an essay with one of the most chilling titles in academic history. Where are they? Why I hope the search for extraterrestrial life finds nothing. His argument was simple and awful. If we discover microbial life on Mars, or in the oceans of Europa, or anywhere else in our solar system, we should not celebrate. We should be terrified, because the existence of independent life nearby would strongly suggest that the early steps, forming life, developing cells, are easy. And if those steps are easy, the filter cannot be there. It must be somewhere ahead of us, waiting. Every sign of life we find elsewhere in the cosmos is, paradoxically, evidence that something terrible is coming for us. Bostrom essentially argued that the best possible news for humanity's long-term survival would be a completely sterile Mars, a dead Europa, a universe where life is so rare that Earth is the only place it ever happened, because that would mean we have already beaten the filter and the staircase ahead is clear. Scholars still argue about where the filter most likely sits. Some point to the origin of life itself, noting that despite decades of trying, no one has ever created life from scratch in a laboratory. The jump from organic chemistry to self-replication might be so improbable that it has only happened once. Others point to the emergence of eukaryotic cells, complex cells with a nucleus, which took nearly 2 billion years to appear on Earth, suggesting it was not easy. Still others point to the evolution of multicellular life, or the development of intelligence, or the transition to technology. Each candidate has defenders, each has weaknesses, and the honest answer, the one that keeps people up at night, is that we do not know. You shift on the grass. The stars above are steady and unmoved by any of this. Somewhere in the back of your mind, a quiet alarm is sounding, the kind you cannot quite locate but cannot ignore either, because you are starting to realize that the Great Filter is not just an abstract philosophical puzzle. It is a description of your future or your past, and you have no way of knowing which. That alarm keeps sounding low and persistent as you lie there trying to figure out which side of the filter you are on. It is like being told there is a trapdoor somewhere in your house, but not being told which room it is in. Every step feels suspicious. Every creak in the floorboard becomes evidence. And the worst part is that the universe is not offering any hints. It is just sitting there, vast and quiet, letting you sweat. So you do what any reasonable person would do at this hour. You start looking at the evidence. Let us take the optimistic case first, because you could use some good news. The argument that the Great Filter is behind us rests on a series of observations about how improbable certain transitions in Earth's history really were. And when you start cataloguing them, you realise that our planet has been running a gauntlet of near impossibilities since the day it formed. Start with the origin of life. As we touched on, nobody has managed to create life from non-life in a laboratory, despite nearly 70 years of trying, since the famous Miller-Urey experiment in 1953, where Stanley Miller and Harold Urey zapped a flask of water, methane, ammonia, and hydrogen with electrical sparks and produced amino acids. Amino acids are the building blocks of proteins, and proteins are essential for life, so the experiment was hailed as a breakthrough. But building blocks are not buildings. Producing amino acids is like producing bricks and then claiming you have built a cathedral. The gap between organic molecules and a functioning self-replicating cell is so vast that some researchers have compared it to a tornado sweeping through a junkyard and assembling a Boeing 747. That analogy was originally used by the astronomer Fred Hoyle, who was arguing against the probability of life arising by chance, and while most biologists think he overstated the case, the core point still stings. Life is staggeringly complex even at its simplest. The most basic bacterial cell contains molecular machinery of such precision that it makes human engineering look like finger painting. Scholars still argue whether life's rapid appearance on Earth, potentially within the first few 100 million years, suggests it is chemically inevitable, or whether we are simply the beneficiaries of a cosmic coin flip that landed right exactly once. Then there is the jump to complex cells. For roughly 2 billion years, life on Earth was exclusively single-celled. Bacteria and archaea ruled the planet with quiet, efficient monotony. And then, somewhere around 2 billion years ago, something happened that appears to have happened exactly once in the entire history of life on Earth. A single archaeal cell engulfed a bacterium, and instead of digesting it, the two formed a partnership. The bacterium became the mitochondrion, the power plant of the cell, and the resulting hybrid became the ancestor of all complex life. Every animal, every plant, every fungus, every protist you've ever seen or eaten or been annoyed by descends from that single event. It is called endosymbiosis, and the fact that it apparently only happened once in 4 billion years suggests it is extraordinarily unlikely. If the origin of complex cells is a filter, it is a brutally effective one. And you remember those mass extinctions we'll get to later, each one a coin flip between continuation and oblivion. You remember that intelligence itself took 3.5 billion years to emerge, and might be an evolutionary dead end dressed up in a lab coat. Every one of these steps is a potential location for the great filter, and every one of them makes you feel a tiny bit better about the future. Because if the hard part is already behind us, the road ahead might be clear. Now here comes the gut punch. Consider the pessimistic case, the argument that the great filter is ahead of us. And this is where finding life on Mars becomes a nightmare scenario. If tomorrow a rover scooping soil from a Martian crater found unmistakable evidence of microbial life, fossilized or worse, still alive, the scientific community would erupt in celebration. Headlines would scream, champagne corks would fly, and Nick Bostrom, sitting somewhere quiet, would feel his stomach drop. Because independent life on Mars would mean that the origin of life is not rare. It is not a cosmic miracle. It is something that happens easily on multiple worlds in the same solar system. And if it happens easily, it cannot be the great filter. The filter must be elsewhere, somewhere later in the chain, somewhere we have not reached yet. Every additional discovery of life beyond Earth tightens the noose. If we find microbes in the subsurface oceans of Europa or Enceladus, that is another early step revealed to be easy. If we detect biosignatures in the atmosphere of an exoplanet, the walls close in further. Each discovery that makes astrobiologists cheer is simultaneously a data point suggesting that the great filter is not in our past but in our future. The universe becomes a room full of civilizations that all made it to roughly our level and then vanished, and we are next in line. There is a strange, almost paradoxical comfort that some people find in this uncertainty. The philosopher John Leslie once compared humanity's situation to that of a person standing in a lineup of prisoners, knowing that 90% of them will be executed at random. Being told that the selection has already happened and you survived is wonderful. Being told it has not happened yet is the worst possible news. But not knowing whether it has happened, that liminal space of ignorance, is where we actually live. And some people find the not knowing oddly peaceful, like standing in a doorway between two rooms, one bright and one dark, and choosing to simply stay in the doorway for as long as possible. You're not sure you find it peaceful. You're finding it mostly chilly lying in this field, wondering whether the Great Filter is a memory or a prophecy. But you do find yourself curious about something. If the filter is behind us, what exactly did we survive? What impossible lucky breaks did Earth stumble into that apparently nobody else managed? The answer, it turns out, is a list so long and so unlikely that it starts to feel like someone rigged the game. The list starts about 4.5 billion years ago, and it starts with violence. You're no longer lying in a field. In your mind, you have been dragged back to the earliest days of the solar system, and it is chaos. The young Earth is a molten nightmare, a ball of liquid rock and toxic gas being pummeled by debris left over from the formation of the sun. And then something extraordinary happens, something so catastrophic that it nearly destroys the planet entirely, and so necessary that you would not exist without it. A body roughly the size of Mars, scientists have named it Theia, after the Greek titan who mothered the moon goddess Selene, which is a poetic touch for an event that was anything but gentle, slams into the young Earth at an oblique angle. The impact is beyond imagination. It liquefies the surface, vaporizes rock, and flings a cloud of molten debris into orbit. Over time, that debris coalesces into the moon, and the moon, it turns out, is not just a pretty thing to write songs about. It is one of the most important objects in the history of life on Earth. The moon stabilizes Earth's axial tilt. Without it, our planet's rotational axis would wobble chaotically over millions of years, swinging from nearly 0 degrees to perhaps 50 or 60 degrees, which would produce climate swings so extreme that complex life would find it nearly impossible to gain a foothold. Imagine seasons where the poles point directly at the sun for months, then plunge into total darkness. The moon keeps that wobble locked to a manageable range of about 22 to 24.5 degrees, which gives us predictable, survivable seasons. Scholars still argue about exactly how unstable Earth's axis would be without the moon. Some recent models suggest the wobble might be less extreme than originally feared, but the consensus remains that the moon has been a crucial stabilizer. It is our cosmic training wheel, and the impact that created it had to hit at precisely the right angle, at precisely the right speed, at precisely the right time. A little harder, and Earth would have been destroyed. A little softer, and the debris would not have reached orbit. The margin of error was, as one planetary scientist put it, uncomfortably thin. Now you add Jupiter to the lucky streak. Jupiter, that massive gas giant sitting out there in the middle of the solar system, looking decorative and smug, is actually functioning as a gravitational bouncer. Its enormous mass, 318 times that of Earth, attracts and deflects a staggering number of comets and asteroids that would otherwise come screaming into the inner solar system and repeatedly sterilize the Earth's surface. Jupiter does not catch everything, obviously. The dinosaurs can attest to that. But without Jupiter, the rate of catastrophic impacts on Earth would be dramatically higher. Some estimates suggest hundreds of times higher, and complex life would be knocked back to the microbial stage so frequently that it might never get the chance to build anything interesting. There is a quirky historical anecdote here. When the comet Shoemaker-Levy 9 broke apart and slammed into Jupiter's atmosphere in 1994, the impact scars were each larger than the entire Earth. Astronomers watched in fascination and quietly thanked gravity that Jupiter was there to take the hit. Then there is plate tectonics. Earth is the only planet in our solar system with active plate tectonics, and this turns out to be far more important than it sounds. The constant recycling of the crust regulates the carbon cycle, which stabilizes the climate over geological timescales. Without plate tectonics, carbon dioxide would build up in the atmosphere unchecked, turning Earth into a Venus-like greenhouse, or it would get locked away in the rocks and the planet would freeze. plate tectonics also builds mountains, creates ocean basins, drives volcanic activity that replenishes atmospheric gases, and generates the magnetic field through the convective churning of the liquid iron core, and that magnetic field is another entry on the lucky list because without it, the solar wind would strip away the atmosphere entirely. Mars had a magnetic field once, it lost it, and then it lost its atmosphere, and then it lost its oceans, and now it is a cold, dead desert with a surface radiation level that would kill you in a matter of months. Earth kept its magnetic field, and everything followed from that. The oxygen catastrophe is another entry that sounds dramatic because it was. Around 2.4 billion years ago, cyanobacteria, simple, mindless photosynthetic organisms, began pumping oxygen into Earth's atmosphere as a waste product. Oxygen was toxic to nearly every living thing on the planet at the time. It was, effectively, the first mass pollution event. Most existing life was poisoned. But the organisms that survived adapted and eventually oxygen-breathing life emerged, the lineage that leads eventually to you. The Great Oxidation Event, as it is formally known, was both a catastrophe and a prerequisite. Without it, complex multicellular life could never have evolved. The energy demands of large active organisms require oxygen metabolism. You're breathing right now because cyanobacteria committed an act of accidental global terrorism 2.5 billion years ago. And then there is Earth's position in the galaxy. We sit in what astronomers call the galactic habitable zone, far enough from the chaotic, radiation-drenched centre of the Milky Way to avoid being sterilized by supernovae and gamma-ray bursts, but not so far out in the sparse galactic suburbs that the heavy elements needed for rocky planets and organic chemistry are unavailable. Our solar system also sits between two major spiral arms, in a relatively calm region called the Orion Spur, which reduces our exposure to the gravitational disruptions and stellar traffic jams that occur within the arms themselves. It is the Goldilocks zone within the Goldilocks zone, a quiet neighbourhood in a quiet part of town in a quiet suburb of a reasonably well-behaved galaxy. You stack all of these factors up: the moon-forming impact, Jupiter's shielding, plate tectonics, the magnetic field, the oxygen event, galactic positioning, and you start to realise something uncomfortable. Each factor on its own might not be vanishingly rare, but the combination of all of them, occurring on the same planet, in the right sequence, at the right time, starts to look like a probability so small it barely deserves the word. Earth did not just win one lottery, it won 12 lotteries simultaneously on the same ticket, while being struck by lightning in a good way. And you are lying in this field, on this impossibly lucky planet, and the grass beneath you feels different now. It feels like it should not be here, like you should not be here, like every blade and every breath is a statistical miracle that the universe did not intend to produce but somehow did. That feeling of improbability deepens as you start thinking about what happened after all those lucky breaks fell into place. Because even with the right planet, the right moon, the right magnetic field and the right cosmic neighbourhood, life on Earth still had to run a gauntlet of destruction so relentless it makes you wonder if the universe was actively trying to take back the gift it had accidentally given. 5 times in the last 540 million years, life on Earth has come within touching distance of total annihilation. 5 mass extinction events so catastrophic that each one wiped out a majority of all species on the planet. They are sometimes called the Big Five, which makes them sound like an accounting firm rather than a series of apocalyptic nightmares, but the name has stuck. And when you look at them one by one, you realise that each one was a filter in its own right, a cosmic audition where most of the cast was cut, and only the understudies survived to stumble onto the next stage. The first major extinction, the Ordovician-Silurian event roughly 445 million years ago killed an estimated 85% of marine species. The likely culprit was a sudden and severe ice age, possibly triggered by a drop in atmospheric carbon dioxide as newly evolved land plants began weathering silicate rocks. The planet froze, the oceans lost oxygen, entire ecosystems collapsed, and then, slowly, life crept back. The survivors diversified. New forms filled the empty niches. The show went on. The second, the late Devonian extinction around 375 million years ago, was slower and messier. It unfolded over millions of years in a series of pulses rather than a single catastrophic blow. Marine life was devastated, particularly reef-building organisms. The causes remain hotly debated. Scholars still argue whether volcanic activity, asteroid impacts, rapid sea level changes, or some combination drove the killing. One fringe hypothesis suggests that the evolution of trees, with their deep root systems breaking apart rock and releasing nutrients into waterways, caused massive algal blooms that sucked oxygen from the oceans. The idea that trees might have caused a mass extinction has a darkly comic quality that feels appropriate for a universe with this sense of humour. The third and the worst is the Permian-Triassic extinction, roughly 252 million years ago. This one is nicknamed the Great Dying, and it earned the title. It killed an estimated 90 to 96% of all species on Earth. 96%. Marine ecosystems were gutted. Terrestrial life was hammered. Insects, which had survived virtually everything else, took massive losses. The cause appears to have been colossal volcanic eruptions in what is now Siberia. The Siberian traps, which release staggering amounts of carbon dioxide and sulfur dioxide into the atmosphere, triggering runaway greenhouse warming, ocean acidification, and oxygen depletion. The Earth became, for a time, very nearly uninhabitable. Recovery took roughly 10 million years, which is the geological equivalent of lying on the bathroom floor after food poisoning and not getting up until next Tuesday. Some paleontologists have noted that if the Permian extinction had been even slightly more severe, there might not have been enough surviving lineage diversity for complex life to recover at all. We came that close to a permanent reset. The fourth extinction, the Triassic-Jurassic event about 201 million years ago, cleared the stage for the dinosaurs. Again, massive volcanic activity, this time the Central Atlantic magmatic province, poisoned the atmosphere and destabilized the climate. The competitors and predators that had been keeping early dinosaurs in check were wiped out, and the dinosaurs, those opportunistic survivors, stepped into the vacancy and dominated for the next 135 million years. And then the fifth, the one everybody knows. 66 million years ago, a rock roughly 10 to 15 kilometers across slammed into what is now the Yucatan Peninsula in Mexico. The Chicxulub impactor hit with a force estimated at 10 billion times the energy of the atomic bomb dropped on Hiroshima. It triggered earthquakes, tsunamis, and a global firestorm. Dust and debris blanketed the atmosphere, blocking sunlight for months or possibly years. Photosynthesis collapsed. Food chains disintegrated. The dinosaurs, those magnificent creatures that had ruled for 165 million years, were gone, along with roughly 75% of all species on Earth. And in the wreckage, small, frightened, furry things, mammals that had spent the age of dinosaurs hiding in burrows and scurrying through underbrush, suddenly found themselves in an empty world full of opportunity. You're one of the descendants of those frightened furry things. Every time you blink or laugh or worry about your phone battery, you're expressing a lineage that survived 5 planetary catastrophes, any one of which could have ended the experiment permanently. And here is where the fringe tidbit gets genuinely unsettling. In the 1980s, Paleontologists David Raup and Jack Sepkoski analysed the fossil record and proposed that mass extinctions appear to occur on a roughly 26 million year cycle. The idea was controversial then, and remains controversial now, but it has never been fully dismissed. Some researchers have suggested the cycle could be driven by the Sun's oscillation through the plane of the Milky Way, which would periodically expose the solar system to denser concentrations of comets in the Oort cloud. Others have proposed a hypothetical companion star to the Sun, nicknamed Nemesis, whose elongated orbit would periodically disturb cometary orbits and send a rain of impacts toward the inner solar system. Nemesis has never been found, and most astronomers consider it unlikely to exist, but the periodicity in the extinction data remains tantalizing. The idea that mass extinctions might run on a schedule, like a cosmic clock ticking down to the next catastrophe, is the kind of thought that makes lying in an open field at night feel slightly less relaxing. Life survived all 5 events. But survived is doing heavy lifting in that sentence. Each time it was the marginal creatures, the overlooked, the small, the lucky, who made it through. The dominant species, the ones running the show, were consistently eliminated, and you cannot help but notice the pattern. The universe seems to tolerate life, but does not tolerate dominance. Every species that rises to the top eventually meets something it cannot overcome. Every empire of scales or feathers or fur eventually falls, and you, lying on this grass, are a member of the current dominant species, the one running the show. The pattern is not comforting. The discomfort follows you as the night deepens and the stars seem to press a little closer. You've been thinking about filters and extinctions and the mathematics of silence, and now your mind wanders to a different kind of explanation. One that does not rely on bad luck or impossible odds or cosmic bottlenecks. One that suggests the universe is not empty because civilizations failed. It is empty because the successful ones learned to shut up. This idea comes from an unlikely source, a Chinese science fiction novelist named Liu Cixin, whose trilogy, beginning with a book called The Three-Body Problem, introduced a concept so elegant and so terrifying that it has leaked out of fiction and into genuine scientific and philosophical discourse. He called it the dark forest theory, and once you hear it, you cannot unhear it. The logic chain is simple, and that is what makes it so devastating. Start with 2 axioms. First, survival is the primary need of every civilization. This seems obvious. Any civilization that does not prioritize its own continued existence will, by definition, not continue to exist. Second, civilizations continuously grow and expand, but the total amount of matter and energy in the universe is finite. Resources are limited, living space is limited. Even in a cosmos as vast as ours, scarcity is real when you're thinking on timescales of millions or billions of years. Now add a problem. When 2 civilizations become aware of each other across interstellar distances, they face an impossible dilemma. Communication takes years, decades, or centuries due to the speed of light. You cannot have a conversation. You cannot negotiate in real time. You cannot verify intentions. And you cannot know whether the other civilization is benevolent, hostile, or simply indifferent in a way that might accidentally destroy you. You also cannot know their technological trajectory. A civilization that seems primitive today might, in a few centuries, develop technology that makes them a threat. And you would have no way of knowing until it was too late. This is where the logic turns cold. If you cannot verify another civilization's intentions, and if you cannot guarantee they will not become a threat in the future, the only rational strategy, the only one that ensures your survival, is to destroy them the moment you detect them. Not out of malice, not out of hatred, simply out of mathematical self-preservation. Because if you do not destroy them, You must assume they are running the same calculation about you, and if they are running the same calculation, they will conclude that they must destroy you first. And if they think you might reach that conclusion, they have even more reason to act preemptively. The chain of suspicion is unbreakable. The game theory is airtight. Liu Cixin compared the universe to a dark forest. Every civilization is a silent hunter moving through the trees. You cannot see them. They cannot see you. And the moment anyone makes a sound, the moment anyone lights a fire, broadcasts a radio signal, sends a probe, every other hunter in the forest swings toward the noise, not to say hello, to eliminate the threat. The dark forest theory is fiction, obviously. Liu Cixin is a novelist, not a physicist. But the underlying logic draws on real game theory, real evolutionary psychology, and real strategic thinking. And it has attracted serious attention from scholars who study the Fermi paradox. The astrophysicist David Brin has explored similar ideas in non-fiction, and the concept of mutually assured destruction between interstellar civilizations has been discussed in academic settings since at least the 1980s. Scholars still argue whether the dark forest logic holds up under scrutiny. Some counter that civilizations advanced enough for interstellar travel would likely have moved beyond the resource scarcity that drives the paranoia. But the defenders of the theory point out that you do not need every civilization to be aggressive. You only need one. One hostile civilization in a galaxy of thousands would be enough to make silence the only safe strategy for everyone else. And here is the quirky footnote that makes this personal. In 1974, the Arecibo radio telescope in Puerto Rico beamed a message toward the globular star cluster Messier 13, roughly 25,000 light-years away. The message contained basic information about humanity, our number system, the structure of DNA, a stick figure of a human being, the population of Earth. It was a deliberate shout into the darkness, a cosmic, "Hello, we're here." The astrophysicist Stephen Hawking, among others, later expressed serious reservations about this kind of messaging. He compared it to indigenous peoples encountering European colonizers and suggested that any civilization advanced enough to visit us would likely treat us the way Europeans treated the civilizations they discovered. The comparison is historically loaded but structurally sound. Every contact between a technologically superior and technologically inferior civilization in human history has gone badly for the inferior one, every single time. And we are not just passively leaking signals. Earth has been broadcasting radio and television transmissions for roughly a century. Those signals travel at the speed of light, expanding in a sphere around our planet. Right now, that sphere is about 200 light-years in diameter, encompassing thousands of star systems. Anything within that bubble with a sufficiently sensitive receiver already knows we're here. If the dark forest theory is correct, we've already made the mistake. We have already lit the fire, and the hunters have already turned toward the sound. You shift on the grass and feel a faint prickle along your arms that has nothing to do with the temperature. The stars are still beautiful, but now, for the first time tonight, you find yourself wondering if beauty is just the bait. If the silence is not emptiness at all but discipline. The sound of 1 billion civilizations holding their breath, hiding in the dark, hoping nobody notices them, and hoping nobody notices you. You lie very still for a moment, as if the universe might actually be listening, and then your mind, because it apparently hates you tonight, moves to an even darker possibility. What if the forest is not just full of silent hunters? What if some of those hunters are not even alive? The concept of self-replicating machines was first seriously proposed by the mathematician John von Neumann in the 1940s and 1950s. Von Neumann was one of those intellects so vast that listing his contributions feels like reading the resume of 5 different geniuses. He helped develop the atomic bomb, laid the foundations of modern computing, invented game theory, and in his spare time worked out the theoretical framework for machines that could build copies of themselves using raw materials found in their environment. He called them self-reproducing automata. Everyone else eventually called them von Neumann probes. The idea applied to space exploration is elegant in a way that is almost offensive. You do not need to build 1 million spaceships, you need to build one. A single probe, equipped with artificial intelligence and the ability to mine asteroids or moons for raw materials, lands in a new star system, builds copies of itself, and sends those copies onward to the next star system. Each copy does the same thing. The process is exponential, even at speeds well below the speed of light, say 10% of light speed, which is ambitious but not physically impossible. A fleet of von Neumann probes could spread across the entire Milky Way galaxy in roughly 1 to 10 million years. That is an eye blink in cosmic terms. A single civilization, launching a single probe, could theoretically explore or colonize every star system in the galaxy without ever leaving home. This is, on its face, a hopeful idea. It means that even civilizations without faster-than-light travel could reach the stars. It is the slow, patient, robotic way to build an interstellar presence. But in 1983, the astronomer Fred Saberhagen had already explored the nightmare version of this concept in his science fiction. Machines programmed not to explore but to destroy. He called them berserkers. And the scientific community, never one to let a terrifying idea go unexplored, eventually developed the concept into a formal hypothesis. The berserker hypothesis proposes that somewhere in the history of the galaxy, a civilization, perhaps one that was paranoid, or that had been attacked, or that simply decided to apply the dark forest logic with mechanical thoroughness, built self-replicating probes designed to seek out and destroy any emerging civilization they detected. These probes would not need to be sophisticated. They would not need to understand culture or morality or the finer points of interstellar diplomacy. They would just need to detect the signatures of technology, radio emissions, atmospheric pollutants, unusual infrared signatures, and then act. Sterilize the planet. Destroy the infrastructure, move on, build more copies, keep hunting. The horrifying efficiency of this scenario is what makes it stick in your brain like a splinter. A single civilization, billions of years ago, could have seeded the galaxy with berserker probes and then gone extinct itself. The probes would not care. They would not mourn their creators. They would simply continue executing their program endlessly, mindlessly, spreading through the galaxy like an immune system attacking any cell that shows signs of independent life. The civilization that built them might be long dead, but their weapons would still be operational, still replicating, still hunting, on a timescale that makes human history look like a single frame in an infinite film, and you would not necessarily know they were there. That is the part that makes astronomers uncomfortable when this topic comes up at conferences, which it does more often than you might expect. A sufficiently advanced berserker probe would not need to be large. It would not need to be visible. It could be sitting in the asteroid belt right now, dormant, waiting for a trigger, a certain type of radio emission, a specific technological signature, a threshold of activity that signals a civilization has become advanced enough to be a threat. Some researchers have half-seriously suggested that we should be scanning our own solar system for anomalous objects that do not behave the way natural asteroids or comets should. The interstellar object Oumuamua, which passed through our solar system in 2017, generated a flurry of exactly this kind of speculation. Its shape was unusual, elongated and flat like nothing we'd seen before. Its trajectory was odd. It accelerated slightly as it moved away from the sun, which could be explained by outgassing from a comet-like surface, but could also, if you squinted hard enough and had read too much science fiction, be explained by something else entirely. The astronomer Avi Loeb at Harvard famously argued that Oumuamua could be an artificial object, a piece of alien technology, perhaps a solar sail. Most of his colleagues disagreed, some of them quite loudly. Scholars still argue about Oumuamua's true nature, and the object itself, indifferent to the debate, has long since left the solar system and vanished into the dark. There is a historical parallel that makes the berserker concept feel less like fiction and more like prophecy. In 1945, humanity detonated the first nuclear weapon at the Trinity test site in New Mexico. Within 20 years, we had built enough nuclear warheads to destroy civilization multiple times over. We created a technology capable of ending our species and then mass-produced it, because that is apparently what we do. Now imagine a civilization 1 million years more advanced than ours. Imagine the weapons they could build. Now imagine those weapons are autonomous, self-replicating, and have been spreading through the galaxy since before our sun ignited. The berserker hypothesis does not require exotic physics or unlikely assumptions. It only requires that one civilization, at some point in the last 13 billion years, made the same kind of decision we made in 1945, but with better technology and worse intentions. You stare at the sky and try not to think about dormant machines sitting in the dark spaces between planets, patient and cold, waiting for a signal that you may have already sent. The crickets are still chirping. A faint rustle in the grass nearby is probably a field mouse and definitely not a self-replicating alien probe. Probably. You tell yourself that and almost believe it. The universe is silent, and now you are starting to understand that silence comes in different flavors. There is the silence of emptiness, where nothing exists to make a sound, and there is the silence of predation, where everything that made a sound has been removed. You're not sure which one you prefer. The field mouse rustles again, closer this time, and you find a strange comfort in its tiny, oblivious presence. It does not know about berserker probes or dark forests. It is just looking for seeds. And that simple, unaware existence nudges your mind toward a gentler hypothesis. One that still explains the silence but does not require anything to be destroyed. What if they are watching? The zoo hypothesis was first formally proposed by the radio astronomer John Ball in 1973, and it offers what might be the most psychologically complex answer to the Fermi paradox. The idea is this: advanced extraterrestrial civilizations are aware of us. They know we are here. They have probably known for a very long time, but they have made a deliberate collective decision not to interfere. They are observing us the way a wildlife biologist observes a troop of chimpanzees in a forest, carefully, quietly, without making contact, because contact would fundamentally alter the behavior of the subjects. We are not alone, we're in a zoo. Or, if you prefer a less patronizing framing, we're in a nature preserve, and the fence is made of policy rather than physics. Ball argued that any civilization advanced enough to reach us would likely be so far beyond our level of development that meaningful communication would be impossible anyway. The gap would not be like the gap between different human cultures. It would be like the gap between humans and ants. You do not try to negotiate trade agreements with an ant colony. You do not attempt to explain democracy to a termite mound. You might study them. You might find them fascinating. But you do not reveal yourself to them, because what would be the point? They could not comprehend you, and your presence would disrupt whatever natural processes they are undergoing. This hypothesis has a certain elegance. It explains the silence without requiring any species to be extinct or hostile. It simply requires that advanced civilizations are patient, ethical, and disciplined enough to leave emerging species alone. And it aligns with a trend we can observe in our own behavior. As human civilization has matured, we have moved, slowly, imperfectly, with plenty of backsliding, toward a greater respect for non-interference with other species. We create national parks, we establish marine sanctuaries, we pass laws against disturbing nesting sites. The trajectory, however uneven, points toward a recognition that observation without interference has value. If we are heading in that direction after a mere 10,000 years of civilization, imagine where a species might be after 10 million. But the zoo hypothesis has its critics, and they raise points that are difficult to dismiss. The biggest objection is what scientists sometimes call the defector problem. For the zoo to work, every advanced civilization in the galaxy would need to agree to the non-interference policy. Every single one. Not just most of them. All of them. Because it only takes one rogue individual, one curious scientist, one rebellious faction, one bored teenager with access to an interstellar transmitter to break the quarantine and make contact. In human history, every secret, every embargo, every quarantine has eventually been broken by someone. The idea that a galactic community could maintain perfect discipline across millions of years, across countless species with different psychologies and motivations, strains credulity. Scholars still argue whether the zoo hypothesis requires an unrealistic level of coordination, or whether a sufficiently advanced civilization might have the means to enforce the quarantine in ways we cannot imagine. Perhaps by monitoring and intercepting any attempts at contact before they reach us. There is a quirky variation on the zoo hypothesis called the planetarium hypothesis, proposed by the philosopher Stephen Baxter in 2001. Baxter suggested that the reason we see no evidence of alien civilizations is that we are not looking at the real universe at all. Instead, we are inside a simulated environment, a planetarium, constructed by advanced beings to keep us contained. The stars we see, the galaxies, the cosmic microwave background radiation, all of it could be a projection, a carefully crafted illusion designed to make us believe we are alone. The real universe, whatever it looks like, might be teeming with life, but we would never know because our entire observable reality is a stage set. This idea sounds absurd until you realize it is essentially unfalsifiable. If the simulation is good enough, there would be no way to detect it from the inside. You cannot test the walls of a room you do not know you are in. And there is another variation, sometimes called the interdict hypothesis, which suggests that a single supremely powerful civilization, perhaps the first one ever to arise in the galaxy, established the non-interference rule and has the technology to enforce it. Think of it as a galactic prime directive, except backed by the kind of power that makes resistance pointless. In this scenario, younger civilizations are not choosing to stay silent. They are being required to. The first civilization, sometimes referred to in these discussions as a hegemon or elder race, might monitor the galaxy for signs of emerging intelligence and ensure that no contact is made until the new species reaches a certain level of development. What that level might be, nobody can say. Perhaps it is mastering interstellar travel. Perhaps it is solving some fundamental problem of ethics or sustainability. Perhaps it is simply surviving long enough to prove you're not going to destroy yourself the moment someone hands you the keys. That last thought lands on you with unexpected weight. Because if there is a test, if the silence is a waiting room, and something out there is watching to see whether humanity passes some threshold before making contact, then everything we do matters in a way that feels simultaneously empowering and paralyzing. Every war, every environmental crisis, every act of cooperation or destruction becomes part of an audition we did not know we were performing, and you have to wonder, lying in this field under this inscrutable sky, whether we are passing or failing. The zoo hypothesis does not require you to be afraid, but it asks something almost harder. It asks you to be humble, to sit with the possibility that you are being observed by intelligences so far beyond your own that you cannot even detect the observation. that every telescope you point at the sky is being watched by something that finds the gesture quaint, that every signal you send is being received, catalogued, and filed away under "not ready yet." The field mouse has gone quiet. Perhaps it found its seed. Perhaps it sensed something larger in the grass and went still, the way small creatures do when they feel watched. You know the feeling. That feeling of being watched shifts into something stranger as your thoughts take another turn, because there is a version of this story where the watchers are not alien civilizations at all. There is a version where the silence makes perfect sense, the emptiness is exactly what you would expect, and the reason is so disorienting that it makes berserker probes and dark forests seem almost cozy by comparison. What if the universe is empty because it was built that way? The simulation hypothesis has been lurking at the edges of philosophy and physics for decades, but it was the philosopher Nick Bostrom at Oxford who gave it its sharpest formulation in 2003. His argument, published in a paper called "Are You Living in a Computer Simulation?", is structured as a trilemma, 3 possibilities, at least one of which must be true. Either virtually all civilizations at our level of development go extinct before developing the technology to run detailed simulations of conscious minds, or virtually all civilizations that do reach that level choose not to run such simulations. Or we are almost certainly living in a simulation right now. The logic is surprisingly hard to escape. If it is possible to simulate a universe with conscious beings inside it, and there is no known law of physics that says it is not, then any civilization that achieves this capability could run millions or billions of such simulations. And if they do, then the number of simulated minds in existence would vastly outnumber the real minds. By sheer statistical weight, any randomly selected conscious being is overwhelmingly more likely to be simulated than real. You, in other words, are more likely to be a process running on some incomprehensible computer than a biological organism lying in an actual field on an actual planet. Now connect this to the Fermi paradox, and the silence clicks into place with eerie neatness. If we are in a simulation, the emptiness of the universe might simply be a design choice. The simulators, whoever or whatever they are, may not have populated the cosmos with other civilizations because doing so was unnecessary for the purpose of the simulation. Simulating an entire universe full of intelligent species would be computationally expensive. Simulating one species on one planet, surrounded by a vast and empty backdrop, would be far cheaper. The stars you see might be rendered, not real. The galaxies might be painted on the ceiling. The cosmic microwave background radiation might be wallpaper, and the silence would not be a mystery at all. It would be a budget decision. This is the kind of idea that either fills you with existential dread or makes you laugh. There does not seem to be much middle ground. But before you dismiss it as the sort of thing that only gets discussed at 3 a.m. by people who have had too much coffee, which is admittedly exactly the scenario we're in, consider that it has attracted serious attention from serious people. The physicist Neil deGrasse Tyson once said, "The probability that we are living in a simulation might be as high as 50%. Elon Musk has stated that the odds of us being in base reality are 1 in billions. The cosmologist Alan Guth has explored the idea that our universe could be a laboratory experiment created by an advanced intelligence. And in 2016, a public debate at the American Museum of Natural History featured prominent physicists arguing both sides of the question, with the kind of intensity usually reserved for disputes about whose turn it is to buy drinks. There is a historical predecessor to simulation theory that adds a strange depth to the conversation. In the 17th century, the philosopher René Descartes proposed his famous thought experiment involving an evil demon, a malicious entity that could, in theory, be feeding you entirely fabricated sensory experiences, making you believe in a world that does not exist. Descartes used this as a starting point for his philosophical method, ultimately arriving at "I think therefore I am" as the one thing the demon could not fake. Bostrom's simulation argument is, in a sense, Descartes' demon updated for the digital age. The demon is now a programmer, the deception is now a software environment, and the escape hatch, the one thing you can be sure of, is considerably less clear. Scholars still argue about whether the simulation hypothesis is genuinely scientific or merely an unfalsifiable philosophical curiosity dressed in the language of computation. The physicist Sabine Hossenfelder has criticized it as pseudoscience, arguing that it makes no testable predictions and therefore does not belong in the domain of physics. Others, including Bostrom himself, have suggested that there might be detectable signatures of a simulation, glitches in the code, so to speak, such as unexpected quantization in the fabric of space-time or anomalies in the distribution of cosmic rays. A 2012 paper by physicists Silas Bean, Zora Dawoodi and Martin Savage proposed a specific experimental test, looking for patterns in the energy spectrum of cosmic rays that would be consistent with a universe simulated on a discrete lattice. The results were inconclusive, which is either disappointing or exactly what you would expect if the simulation is well designed. And here is the quirky detail that makes this whole thing feel like a nested joke. If we are in a simulation, and we eventually develop the ability to run our own simulations containing conscious beings, then we become simulators ourselves, creating universes inside a universe that is itself inside another universe. The recursion is dizzying. It is turtles all the way down, except the turtles are server farms, and each layer would presumably face its own version of the Fermi paradox, its own empty sky, its own late-night existential spiral in a field that may or may not be made of actual grass. You reach down and touch the grass. It feels real. The dampness, the texture, the faint smell of earth and chlorophyll. Your fingers report solid information. Your brain processes it with the confidence of billions of years of evolved sensory machinery. But the simulation argument whispers that this is exactly what a good simulation would feel like, indistinguishable from reality. Because if it were distinguishable, it would not be a very good simulation. The stars overhead continue their slow rotation, indifferent to whether they are fusion reactors or pixels. And you find that the question of whether you are real or rendered matters less than you expected. Because either way, you're here. Either way, you are conscious. Either way, the night is beautiful and the silence is vast, and you're a small, wandering thing in the middle of something enormous that you do not fully understand. And maybe that is the point. Or maybe it is just the loading screen. The loading screen joke lingers as a faint smile on your face, but the night is not done with you yet. Because there is a concept lurking in the basement of physics that makes simulation theory look positively comforting by comparison. It is called the Boltzmann brain problem, and it is the kind of idea that physicists bring up when they want to make other physicists visibly uncomfortable. It starts with a man named Ludwig Boltzmann, an Austrian physicist working in the late 19th century, who helped lay the foundations of statistical mechanics and thermodynamics. Boltzmann was brilliant, passionate, and deeply troubled. He struggled with depression throughout his life and ultimately took his own life in 1906, partly because many of his contemporaries refused to accept the existence of atoms, which he had spent decades trying to prove were real. History vindicated him completely, but too late for him to know it. His gravestone in Vienna bears the inscription of his most famous equation, S equals K log W, which describes the relationship between entropy and the number of possible microscopic states of a system. It is arguably the most important equation in thermodynamics, and it leads, by a chain of logic that Boltzmann himself never anticipated, to one of the most unsettling ideas in all of science. Here is the chain. Thermodynamics tells us that the universe tends toward increasing entropy, increasing disorder. A glass of ice water will always warm up to room temperature. A sandcastle will always crumble. A shuffled deck of cards will never spontaneously arrange itself into perfect order. The universe, left to its own devices, moves relentlessly from structure to chaos, from organization to randomness, from meaning to noise. This is the second law of thermodynamics, and it is as close to an absolute rule as physics has to offer. But, and this is a very large and very uncomfortable but, statistical mechanics also tells us that entropy decreases are not impossible. They are merely extraordinarily improbable. Given enough time, random fluctuations will produce temporary pockets of low entropy. The glass of warm water will, if you wait long enough, spontaneously separate into hot and cold regions. The shuffled deck will, given a truly absurd number of shuffles, eventually land in perfect order. And given enough time and enough random quantum fluctuations in an otherwise dead, featureless universe, a conscious mind will spontaneously pop into existence. Not a body, not a planet, not a civilization, just a brain. A single, isolated, disembodied consciousness, complete with false memories of a life it never lived, floating in the void for a fraction of a second before dissolving back into entropy. This is a Boltzmann brain, and the problem is not that it could happen. The problem is that, according to certain cosmological models, it is overwhelmingly more likely to happen than what we think happened, namely the emergence of consciousness through billions of years of stellar evolution, planetary formation, abiogenesis, and biological evolution. Think about that for a moment. The amount of stuff that had to happen for you to be lying in this field, the Big Bang, the formation of galaxies, the lucky breaks of Earth's history, the 5 mass extinctions, the rise of mammals, the evolution of primates, the development of language and agriculture and eventually YouTube, is so cosmically expensive, so thermodynamically extravagant, that a random fluctuation producing a single brain with the illusion of all those memories would be far cheaper, trillions of times cheaper. And in a universe that will exist for unfathomable stretches of time after all the stars have died, those random fluctuations will have essentially infinite opportunities to occur. So here is the question that makes physicists reach for a drink. Are you a real observer, the product of 13.8 billion years of cosmic evolution on a real planet in a real galaxy? Or are you a Boltzmann brain, a momentary fluctuation in the quantum vacuum, hallucinating an entire universe that does not exist, complete with memories of a childhood, a favourite song, and a night spent lying in a field looking at stars that are nothing more than electrical artifacts in a temporary pocket of accidental consciousness? The honest answer is that you cannot tell. From the inside, both experiences would be identical. Your memories feel real. Your senses report consistent information. The stars appear to follow predictable physical laws, but a Boltzmann brain with sufficiently detailed false memories would feel exactly the same way. You would have no way of knowing the difference. Scholars still argue about whether the Boltzmann brain problem is a genuine crisis for cosmology or a reductio ad absurdum, an indication that something is wrong with the assumptions that lead to the conclusion rather than a real description of reality. The physicist Sean Carroll has argued that any cosmological model that predicts more Boltzmann brains than real observers is, by definition, a bad model and should be discarded. Others counter that discarding models simply because their conclusions are disturbing is not how science is supposed to work. The debate is ongoing, technical, and occasionally heated in the way that only arguments between theoretical physicists can be. There is a quirky historical footnote that ties this back to Boltzmann himself. In his own time, Boltzmann struggled with the question of why the universe appears to have started in such a low entropy state. Why, in other words, things were ever organised enough for stars and planets and people to form in the first place. He proposed, tentatively, that our observable universe might be a random fluctuation in a much larger, much older cosmos that has already reached thermal equilibrium. We just happen to be in the fluctuation. It was a remarkable intuition for the 1890s, and it planted the seed that would eventually grow a century later into the Boltzmann brain nightmare. You press your palms into the grass and feel the cool blades between your fingers. You're choosing to believe this is real, not because you can prove it, but because the alternative is a loneliness so profound it makes the Fermi paradox seem like a mild social inconvenience. A Boltzmann brain has no universe, no stars, no field, no crickets, no other minds. It has only itself, flickering briefly in an eternity of nothing, mistaking its own dissolution for a sunset. The night is still beautiful. You hold on to that. You hold on to the beauty and let your mind drift from the philosophical back to the physical. Because while Boltzmann brains and simulations play games with the nature of reality itself, there is something concretely, measurably, photographically terrifying about the actual structure of the universe that requires no speculation at all. You just have to look at it. The universe, it turns out, is not a random scattering of galaxies floating evenly through space, like dust motes in a sunbeam. It has architecture, and that architecture looks like something alive. Starting in the late 1970s and accelerating through the 1980s and 1990s, astronomers began mapping the three-dimensional distribution of galaxies in ever greater detail. What they found was not the smooth, homogeneous cosmos that many had expected. Instead, galaxies are arranged along vast filaments, long, thin threads of matter stretching hundreds of millions of light-years across, connecting dense nodes where galaxy clusters congregate like cities at the intersections of highways. Between these filaments lie the voids, not the casual gaps you might imagine between neighbouring galaxies, but genuine yawning absences of matter on a scale that strains the human capacity for spatial reasoning. This structure is called the cosmic web, and when you see images of it, produced by surveys like the Sloan Digital Sky Survey or simulations like the Millennium Simulation, it looks disturbingly organic. It looks like the neural network of a brain. It looks like the mycelium network of a fungus spreading through soil. It looks like the pattern of blood vessels branching through tissue. The resemblance is not just poetic. In 2020, an astrophysicist named Franco Vazza and a neuroscientist named Alberto Felletti published a paper comparing the structural properties of the cosmic web to the neural network of the human brain, and found striking mathematical similarities in their complexity, connectivity, and information capacity. The universe at its largest scale and the brain at its smallest share an organizational logic that nobody fully understands. Scholars still argue about whether this similarity is a deep clue about the fundamental nature of networks, or simply a coincidence arising from the mathematics of self-organizing systems. Either way, looking at the images side by side produces a sensation that is difficult to name but impossible to ignore. The filaments of the cosmic web are where the action is. They contain the overwhelming majority of the universe's ordinary matter: galaxies, gas, dust, stars, and presumably whatever civilizations might exist. But the filaments are thin, cosmically thin. They are the embroidery on a vast dark canvas, and the canvas, the voids, dominates the picture. Remember the Bota's void from earlier, that 330 million light-year sphere of almost nothing? It is not alone. The universe is riddled with supervoids, and some of them are even larger and emptier than Bota's. The KBC void, identified in 2013, may extend up to 2 billion light-years across, making it one of the largest known structures, or rather anti-structures, in the observable universe. We're inside it. Our own galaxy, the Milky Way, sits within a region of space that is significantly less dense than the cosmic average. We live in a void. Not the most dramatic void, not the emptiest, but a void nonetheless. There is something darkly funny about spending centuries wondering why the universe seems so empty, and then discovering that we happen to live in one of the empty parts. It is like complaining about a restaurant being dead on a Tuesday night when you're sitting in the closed section. But the void that has generated the most scientific anxiety is the one that should not exist at all. In 2004, astronomers analysing data from the Wilkinson Microwave Anisotropy Probe, a satellite designed to map the cosmic microwave background radiation, that ancient afterglow of the Big Bang, discovered an unusually cold spot in the constellation Eridanus. Cold spots in the cosmic microwave background are not uncommon. They correspond to regions of slightly lower density in the early universe. But this one was enormous and anomalously cold, far more so than standard cosmological models predicted. Further investigation revealed that the cold spot aligns with a massive supervoid, the Eridanus supervoid, roughly 1.8 billion light-years across and remarkably underpopulated with galaxies. The problem is that the standard model of cosmology, the lambda-CDM model, which has been spectacularly successful at explaining nearly everything else about the universe, does not comfortably accommodate a void this large and this empty. The probability of such a structure forming through normal gravitational processes is extremely low. Some estimates place it at less than 2%, though the exact figure depends on assumptions that researchers continue to debate. Some scientists have proposed exotic explanations, that the cold spot is evidence of a collision with another universe in a multiverse scenario, or that it represents a fundamental asymmetry in the fabric of space-time. Others argue that it is simply a statistical outlier, the cosmic equivalent of rolling double sixes 10 times in a row. Unlikely, but not impossible. Scholars still argue, papers are published, and the Eridanus supervoid sits there, cold and inexplicable, like a hole in the wallpaper of reality. What all of this means for the question of cosmic emptiness is both straightforward and deeply strange. The universe is not uniformly empty. It is structured emptiness. It is organised absence. The voids are not random blank spaces. They're shaped by the same gravitational forces that built the filaments, carved out by dark matter and dark energy into a foam-like geometry, where the bubbles are hundreds of millions of light-years across, and the walls are gossamer thin threads of galaxies separated by distances that light itself takes billions of years to cross. You're lying in your field, on a planet, orbiting a star, in a galaxy, embedded in a filament, bordering a void, inside a larger void, all of it suspended in a web of matter so sparse that it makes a cobweb look like a brick wall. The ground beneath you feels solid, but it is a tiny knot of matter clinging to a thread stretched across an abyss. And the abyss is not just empty, it is structured to be empty. The architecture of the cosmos is an architecture of absence, and you are living in one of the few places where the absence briefly relents. A cloud drifts across part of the sky, obscuring a handful of stars, and for a moment the darkness in that patch feels thicker, more deliberate, as if the void has always been there, patient and enormous, and the stars were the interruption. The cloud passes, the stars return, and you find yourself thinking about what is hiding in all that structured emptiness. Because the voids, as terrifying as they are only part of the story. The cosmic web, the filaments, the galaxy clusters, all of that visible architecture accounts for roughly 5% of the total content of the universe. 5%. Everything you have ever seen, touched, orbited, or pointed a telescope at is a rounding error. The rest is something else entirely, and most of it is something we cannot see. Dark matter makes up approximately 27% of the universe's total mass energy content. That means there is about 5 times more dark matter than ordinary matter, the protons, neutrons, and electrons that compose every star, every planet, every grain of sand, every cell in your body. Dark matter does not emit light. It does not absorb light. It does not scatter light. It passes through ordinary matter like a ghost walking through a wall. The only way we know it exists is by its gravitational effects, and those effects are everywhere. The story begins in the 1930s, when the Swiss astronomer Fritz Zwicky, a man whose contributions to astrophysics were matched only by his talent for insulting his colleagues, whom he reportedly called spherical bastards because, he explained, they were bastards no matter which direction you looked at them, was studying the Coma cluster, a massive collection of galaxies about 320 million light-years away. Zwicky measured the velocities of galaxies within the cluster and found that they were moving far too fast. Based on the visible mass of the cluster, the galaxies should have been moving slowly, held in gentle gravitational embrace. Instead, they were screaming around like cars on a racetrack. The gravitational pull of the visible matter was nowhere near strong enough to hold the cluster together. Something unseen, something with enormous mass, had to be providing the extra gravity. Zwicky called it dunkel Materie, dark matter. The scientific community largely ignored him for decades. Zwicky was brilliant but difficult, and his claim seemed too extraordinary. It was not until the 1970s that the astronomer Vera Rubin, working with Kent Ford at the Carnegie Institution, produced evidence so compelling that dark matter could no longer be dismissed. Rubin studied the rotation curves of spiral galaxies, the speeds at which stars orbit the galactic center at various distances. According to Newtonian gravity and the visible mass of the galaxies, stars at the outer edges should orbit more slowly than stars near the center, the same way outer planets in our solar system orbit more slowly than inner ones. But Rubin found that the rotation curves were flat. Stars at the edges were moving just as fast as stars near the center. The galaxies were spinning in a way that was physically impossible given their visible mass. Something massive and invisible was embedded in and around every galaxy she examined, providing the gravitational scaffolding that held things together. Rubin's work transformed cosmology, though she never received the Nobel Prize for it, a fact that many in the scientific community consider a significant oversight. She passed away in 2016. The Vera C. Rubin Observatory in Chile, currently under construction, and expected to revolutionize our understanding of dark matter when it begins operations, was named in her honor. And yet, despite decades of effort, nobody knows what dark matter actually is. The leading candidates are weakly interacting massive particles, or WIMPs, hypothetical particles that interact with ordinary matter only through gravity and the weak nuclear force. Enormous, expensive experiments have been built to detect them. Tanks of liquid xenon buried deep underground, shielded from cosmic rays, waiting for a single dark matter particle to bump into a single xenon atom and produce a detectable flash. So far, nothing. The Large Hadron Collider at CERN has searched for dark matter particles in high-energy collisions. Nothing. Scholars still argue about whether WIMPs are the answer, whether dark matter might instead be composed of axions, another hypothetical particle, far lighter and even more ghostly, or whether the entire concept is wrong and what we are actually seeing is a modification of gravity itself at large scales. The modified gravity camp is a minority but a persistent one, and they raise points that the mainstream cannot entirely dismiss. Here is what we do know. Dark matter forms a vast invisible web that mirrors and underlies the visible cosmic web. The filaments of galaxies that you learned about trace the underlying dark matter, scaffolding the way Christmas lights trace the branches of a tree. The tree is dark matter. The lights are us. Without the dark matter skeleton, the visible universe would not have its structure. Galaxies would not have formed. Stars would not have coalesced. Planets would not have congealed from the gravitational collapse of gas and dust. You would not be lying in a field. The scaffolding of everything you know is made of something you cannot detect. There is a quirky way to think about this that captures the strangeness. Imagine you moved into an apartment and discovered that 85% of the furniture was invisible. You could not see the couch, but you kept bumping into it. You could not see the table, but objects placed in mid-air stayed suspended. The walls were mostly transparent. The floor was real, but everything underneath it was hidden. You would quickly realize that you were not the primary tenant of this space. You were the minor occupant of someone else's house. Dark matter does not interact with us. It does not care about us. It was here first, it outweighs us 5-1, and it shaped the very structures we inhabit. We are the afterthought in a universe built for something we cannot perceive. You lie in the grass and feel the planet's gravity holding you gently to its surface, and you realize that even that gravity is partly a gift from the invisible. The dark matter halo surrounding the Milky Way extends far beyond the visible disk of stars, enveloping the galaxy in a sphere of unseen mass. You're embedded in it right now. It is passing through your body at this very moment, millions of dark matter particles streaming through every square centimetre of you every second, never touching a single atom, never leaving a trace. You're haunted by something you cannot feel, and it is the majority of everything that exists. The invisible majority holds you for a moment, dark matter streaming through your body like wind through a screen door. And then your mind reaches for the other piece of the cosmic puzzle, the one that is even stranger, the one that is not just invisible but actively hostile to everything you care about. Because if dark matter is the unseen scaffolding holding the universe together, dark energy is the force tearing it apart. Dark energy accounts for roughly 68% of the total mass energy content of the universe. Add that to the 27% that is dark matter and ordinary matter. You, the stars, the galaxies, the cosmic web, everything that has ever been photographed or measured or loved, comes to about 5%. You're living in a universe where 95% of everything is something you do not understand. And the 68% that is dark energy is not just mysterious, it is working against you. The story starts in 1998 with two independent teams of astronomers studying a particular type of stellar explosion called a Type 1 supernova. These explosions are useful because they all reach roughly the same peak brightness, which makes them excellent cosmic yardsticks. By measuring how bright a Type 1 supernova appears from Earth, and comparing that to how bright it actually is, you can calculate how far away it is. And by measuring the redshift of the light, how much the wavelength has been stretched by the expansion of the universe, you can determine how fast the space between us and the supernova is expanding. The two teams, the Supernova Cosmology Project and the High Z Supernova Search Team, expected to find that the expansion of the universe was slowing down. Gravity, after all, should be pulling everything back together, like a ball thrown upward, gradually losing speed. They found the opposite. The expansion was accelerating. Distant supernovae were dimmer than expected, meaning they were farther away than they should have been, meaning the universe was not just expanding, but expanding faster and faster over time. Something was pushing. Something was counteracting gravity on the largest possible scales and winning. The discovery was so shocking that both teams initially assumed they had made an error. They checked and rechecked their data. They consulted each other, despite being rival teams. The result held. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees shared the Nobel Prize in Physics for the discovery. And the mysterious something doing the pushing was given the name dark energy, which is a name that sounds like it should come with a cape and an evil laugh, but is actually an admission of ignorance. We call it dark because we cannot see it. We call it energy because it acts like energy. Beyond that, we are guessing. The most popular explanation is that dark energy is a property of space itself, Einstein's cosmological constant, a term he originally added to his equations of general relativity to keep the universe static, and later called his greatest blunder when it was discovered that the universe was expanding, turns out to describe something real. Empty space is not truly empty. It has an intrinsic energy density, and as the universe expands and more space is created, more dark energy comes into existence. The more space there is, the more dark energy there is, and the faster the expansion accelerates. It is a feedback loop with no breaks. Scholars still argue about whether the cosmological constant is truly constant, or whether dark energy might be changing over time, a possibility sometimes called quintessence. And the answer has profound implications for the ultimate fate of everything. Here is what the acceleration means for the emptiness you have been contemplating all night. The universe is getting lonelier. Right now, from our position in the Milky Way, we can observe galaxies stretching out to a distance of about 46 billion light-years in every direction. The observable universe. Light from those distant galaxies has had 13.8 billion years to reach us, and the expansion of space has carried those galaxies even farther away during the journey. But the accelerating expansion means that there are galaxies whose light will never reach us. They are receding faster than the speed of light, not because they are moving through space faster than light, which is impossible, but because the space between us and them is expanding faster than light can cross it. They have passed beyond our cosmic horizon. They are gone, not destroyed, not extinguished, simply unreachable, lost to us forever, and the horizon is shrinking. As the expansion accelerates, more and more galaxies will slip beyond the observable boundary. The number of galaxies we can see will decrease over time. In roughly 100 billion years, a long time by human standards but a modest span by cosmic ones, almost every galaxy beyond our local group will have vanished beyond the horizon. The night sky, which currently contains the light of 2 trillion galaxies, will eventually contain only the aging remnants of the Milky Way and the handful of galaxies gravitationally bound to it. A civilization arising at that distant future time would look up and see a universe that appears to contain only a single galaxy, surrounded by infinite darkness. They would have no way of knowing that trillions of galaxies once filled the sky. The evidence would be gone. The light would be unreachable. They would construct a cosmology based on the information available to them and conclude, incorrectly but reasonably, that the universe was small and lonely and had always been that way. There is a quirky and haunting thought experiment by the physicists Lawrence Krauss and Robert Scherer that explores this in detail. They pointed out that future civilizations would not only lose sight of distant galaxies, but would also lose access to the cosmic microwave background radiation, the single most important piece of evidence for the Big Bang. Without it, future scientists would have no way of deducing that the universe had ever been hot, dense, or expanding. The Big Bang itself would become undetectable. The history of the cosmos would be erased by its own expansion. We happen to live in the one era of cosmic history where the evidence is still visible. We are in the sweet spot, the narrow window where the universe still remembers its own past, and that window is closing. You stare at the stars and realize you're looking at a vanishing act in slow motion. Every photon reaching your eyes tonight is a message from a universe that is methodically deleting itself. The loneliness you feel is not a metaphor, it is a forecast. The forecast stretches out ahead of you like a road with no turns, and you follow it because your mind has committed now and there is no looking away. The accelerating expansion is bad enough, But the expansion is not the ending. It is just the mechanism that delivers you to the ending. And the ending, the real ending, the one that physics insists upon with the cold certainty of a mathematical proof, is the heat death of the universe. The name is misleading. It will not be hot. It will be the opposite of hot. It will be the most profoundly cold, still, featureless state that matter and energy can achieve. It is the point at which entropy, that relentless tendency toward disorder that has been running the show since the Big Bang, finally wins. Not partially, not temporarily, completely and forever. You already know the second law of thermodynamics from earlier tonight, when we talked about Boltzmann and his tragic equation. Energy flows from hot to cold. Structure decays into randomness. Every process in the universe increases the total entropy of the system. Your body does this every time it metabolizes food. It takes ordered chemical energy and converts it into heat, motion, and waste, all of which are less organized than what you started with. Stars do this on a grander scale, converting nuclear fuel into light, heat, and heavier elements, spreading energy outward until the fuel is spent. Every galaxy, every star, every living thing is a temporary pocket of order swimming against a tide of entropy, and the tide always wins. Always. The timeline of the heat death is measured not in billions of years, but in numbers so large they require their own notation. Let us walk through it, because the universe has the patience even if you do not. In roughly 5 billion years, the sun will exhaust its hydrogen fuel, swell into a red giant and swallow Mercury, Venus, and possibly Earth. Whether it consumes our planet or merely scorches it into a cinder is a detail scholars still argue about, though either outcome makes the distinction somewhat academic from a human perspective. This sun will then shed its outer layers, leaving behind a white dwarf, a dense glowing ember about the size of Earth, but with the mass of a star. It will cool slowly, radiating away its remaining heat over trillions of years. In about 100 billion years, as we discussed, the accelerating expansion will have carried nearly all galaxies beyond the observable horizon. The Milky Way, having merged with Andromeda and a few smaller companions to form a single large elliptical galaxy, sometimes called Milkdromeda, a name that sounds like a rejected breakfast cereal, but is the actual term some astronomers use, will be an island of aging stars in an otherwise empty observable universe. In roughly 100 trillion years, that is a 1 followed by 14 zeros, the last stars will die. Star formation requires gas clouds dense enough to collapse under their own gravity, and by this point the available gas will have been used up or dispersed beyond recovery. The universe will enter what is sometimes called the degenerate era, populated only by the cooling corpses of dead stars, white dwarfs fading to black dwarfs, neutron stars slowly spinning down, and black holes growing ever more dominant as they sweep up whatever remnants drift too close. There is a wonderfully grim detail here. No black dwarf has ever been observed, because the universe is not old enough for any white dwarf to have cooled completely. They are a prediction, not an observation. The first black dwarfs will not appear for perhaps a quadrillion years. The universe has not even begun to be truly dark yet. In roughly 10 to the 40th power years, a number so large it looks like a typo, protons themselves may decay. This is speculative, as proton decay has never been observed, and some models of particle physics do not predict it. But if protons are unstable, even with half-lives of unimaginable length, then eventually every atom in the universe will dissolve. Every piece of matter that was not already inside a black hole will simply come apart at the subatomic level. The degenerate era will give way to the black hole era, in which the only significant objects in the cosmos are black holes, spinning, evaporating, and completely alone. and then even the black holes will die. Stephen Hawking demonstrated in 1974 that black holes are not truly black. They emit a faint radiation, now called Hawking radiation, caused by quantum effects near the event horizon. This radiation carries away energy, which means the black hole slowly loses mass. For stellar mass black holes, this process takes roughly 10 to the 67th power years. For supermassive black holes, the kind that anchor galaxies, it takes perhaps 10 to the 100th power years, a 1 followed by 100 zeros, a span of time called a Google year. After that, the last black hole in the universe will evaporate in a final faint whisper of radiation, and then there will be nothing left. Nothing structured anyway. The universe will still exist technically. It will be an incomprehensibly vast, incomprehensibly cold, incomprehensibly dark expanse of scattered photons and subatomic particles, each one so far from its nearest neighbour that no interaction between them will ever occur again. The temperature will asymptotically approach absolute zero. No work can be performed, no information can be processed, no thought can be sustained. Entropy will have reached its maximum value, and the second law of thermodynamics will have nothing left to enforce because there is nothing left to decay. This is the heat death, not a bang, not a dramatic cosmic finale, just a slow, patient, inevitable dimming that takes longer than any number you've ever used in your life and ends in a silence so absolute it makes the current silence of the cosmos, the one that started this whole conversation, seem positively chatty. You breathe in, you breathe out. Each breath is a temporary reversal of entropy, a small warm rebellion against the thermodynamic fate of everything. Your body is a furnace of chemical order that will burn for a few more decades, if you are lucky, before surrendering its borrowed energy back to the void, and you find yourself thinking that maybe the emptiness of the universe is not a mystery to be solved. Maybe it is a preview. The silence is not where the universe is going. It is where the universe already mostly is. And the pockets of noise, the stars, the galaxies, the civilizations asking where everybody went, are the anomaly. The brief, beautiful interruption. The brief, beautiful interruption. You sit with that phrase for a while, feeling it settle into your chest alongside the cool night air, and then, because the universe apparently has one more twist to offer before it lets you rest, your mind circles back to the Fermi paradox with a new angle, one that does not depend on filters or forests or simulations or entropy, one that depends on timing. In 2021, the economist Robin Hanson, the same Robin Hanson who gave us the Great Filter back in 1996, because apparently one civilization-shaking hypothesis per career was not enough for him, published a paper with Daniel Martin and Calvin McCarter introducing a model they called grabby aliens. And it reframes the entire question of cosmic silence in a way that is both mathematically elegant and deeply, quietly alarming. The core insight is deceptively simple. What if the reason we do not see aliens is not that they do not exist, but that they have not reached us yet? Hanson's model divides potential civilizations into two categories. Quiet civilizations are ones like us, civilizations that exist but have not expanded beyond their home systems in any visible way. They do not reshape galaxies. They do not build structures detectable across cosmic distances. They sit on their planets and wonder about the silence, and maybe make podcasts about it. Grabby civilizations, by contrast, are ones that expand aggressively, colonizing star systems, rearranging matter, converting entire regions of space into something visibly altered. They grab territory, they leave marks, and once they start expanding, they do not stop. The model assumes that grabby civilizations arise randomly throughout the universe at some low but non-zero rate, and that once they appear, they expand outward at some significant fraction of the speed of light. As they expand, they fill the volume of space around them, making it impossible for new civilizations to arise independently in that territory, either because they colonize the habitable worlds directly or because they alter the environment in ways that preclude independent development. The grabby civilizations in Hansen's model are like ink drops in water, expanding spheres of influence that eventually fill the entire volume. Here is where the timing argument gets interesting. If you run the math, and Hansen's paper does with considerable rigour, you find that the expected arrival time of the nearest grabby civilization depends on how many such civilizations exist and how fast they expand. And the model produces a striking prediction. We should expect to be relatively early. Specifically, we should expect to have appeared just before the expanding wavefronts of grabby civilizations reach our region of space. The reason is anthropic. If grabby aliens had already reached us, we would not have arisen independently. We can only exist in a region of space that has not yet been claimed. The fact that we are here, asking the question, is itself evidence that the grabby aliens have not arrived yet, but the model suggests they are on their way. Hansen estimated that grabby civilizations may currently control roughly 40 to 50% of the reachable universe, with their expanding fronts converging on the remaining unclaimed territory. We happen to be in one of the remaining gaps, a pocket of space where no grabby civilization has yet arrived. But the gaps are closing. The model suggests that within a few 100 million to a few billion years, the nearest grabby civilization's expansion front will reach us. At that point, our window of independent existence closes. This reframes the emptiness in a way that feels less like a graveyard and more like a countdown. The universe is not empty because everyone is dead. It is empty here because the wave has not hit us yet. We are standing on a beach watching a calm ocean, not realizing that somewhere beyond the horizon, a tsunami is already moving. Scholars still argue about the assumptions underlying the grabby aliens model. The expansion speed, the rate of civilization emergence, the definition of grabby, all of these are debatable parameters that significantly affect the output. Some critics argue that the model assumes expansion is inevitable for sufficiently advanced civilizations, which may not be true. Perhaps most civilizations that could expand choose not to, preferring contemplation over colonization, sustainability over sprawl. Others counter that it only takes one grabby species to change the equation, and in a universe with trillions of potential origins, the probability of none of them being expansionist approaches zero. There is a quirky implication of the model that ties back to something we discussed much earlier tonight. Remember the Great Filter? Hansen's grabby aliens model actually provides a partial resolution. If the universe is being parcelled out by expanding civilizations, then the reason for the silence is not that civilizations fail. It is that they succeed, somewhere else, far away, beyond our current ability to detect them. The Great Filter might not be a wall, it might be a race, and we might have entered the race late, just in time to see the leaders disappearing around the final curve. The historical parallel here is the one that European explorers would recognise, for better or worse. In the 15th and 16th centuries, European powers began expanding outward across the globe, claiming territory, establishing colonies, converting indigenous lands into extensions of distant empires. From the perspective of an isolated civilization in the interior of a continent that had not yet been reached, say, a community deep in the Amazon or the highlands of Papua New Guinea, the world would have appeared empty, quiet, no evidence of other great powers, no ships on the horizon. The silence would have been genuine, and it would have been temporary. The explorers were coming, they just had not arrived yet. You lie in the grass and think about wavefronts. invisible, expanding spheres of alien influence moving through the galaxy at some fraction of the speed of light. Not malicious necessarily, not berserker probes or dark forest hunters, just expansionist, thorough, inevitable, and somewhere out there, beyond the range of your telescopes and your imagination, the edge of someone else's civilization is moving toward this quiet little arm of the Milky Way, where a small, curious, slightly anxious species is lying in a field, looking at stars and wondering why nobody has called. Maybe nobody has called because they're still en route, and maybe the ringing will be louder than you expect. The ringing has not started yet though, and in the meantime you are part of a species that has spent the last 6 decades doing something either incredibly brave or incredibly foolish, depending on which hypothesis from tonight turns out to be correct. You have been searching. Actively, deliberately, with radio dishes and algorithms and optimism, you've been reaching into the silence and asking it to answer. The modern search for extraterrestrial intelligence begins, fittingly, with the same Frank Drake whose equation we explored earlier tonight. In 1960, a year before he wrote the equation actually, Drake conducted the first systematic SETI experiment. He called it Project Ozma, named after the princess in L. Frank Baum's Oz books, because he wanted a name that evoked a distant, exotic, unreachable land. Using the 85-foot radio telescope at Greenbank, West Virginia, he pointed at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for artificial signals at a frequency of 1420 MHz, the natural emission frequency of hydrogen, which had been suggested as a likely interstellar communication channel because any technologically competent civilization would know about it. He listened for roughly 200 hours over 4 months. He heard nothing. Well, almost nothing. There was one moment of excitement, a strong pulsing signal that sent the team scrambling, but it turned out to be a high-altitude aircraft. The universe remained silent, and Drake moved on to designing his equation, organising conferences and becoming the founding figure of a field that has been listening to static for over 60 years. But SETI did not stop with Ozma. It grew. Throughout the 1970s and 1980s, various programs expanded the search, scanning more stars, more frequencies, more of the sky. NASA briefly funded a SETI program in 1992 called the High Resolution Microwave Survey, which was promptly defunded by Congress in 1993 after Senator Richard Bryan of Nevada declared that the Great Martian Chase had found nothing and was a waste of taxpayer money. The quote became a minor legend in the SETI community, a reminder that searching for cosmic neighbours is a hard sell when terrestrial budgets are tight. The programme's cancellation forced SETI into the private sector, where it has lived ever since, funded largely by donations and the occasional tech billionaire. The most famous moment in SETI's history arrived on August 15th, 1977, and it happened almost by accident. Jerry Eman, a volunteer researcher working with Ohio State University's Big Ear radio telescope, was reviewing printouts of signal data when he spotted something extraordinary. A strong narrowband signal, lasting 72 seconds, originating from the direction of the constellation Sagittarius. The signal was at the hydrogen frequency. It was 30 times louder than the background noise. It matched every characteristic that scientists had predicted an artificial interstellar signal would have. Eman circled the reading on the printout and wrote a single word in the margin: "Wow." The wow signal, as it inevitably became known, has never been satisfactorily explained. It was never detected again, despite numerous follow-up observations pointing at the same region of sky. Some researchers have proposed natural explanations: a comet releasing hydrogen gas, an unusual reflection of a terrestrial signal off space debris, but none have been universally accepted. Scholars still argue about whether the WOW signal was a genuine alien transmission, a natural astronomical phenomenon, or an instrumental artifact. It sits in the annals of SETI like an unopened letter found on a doorstep, tantalizing, frustrating, and maddeningly singular. In 2015, the search received its largest ever injection of resources when the Russian-Israeli billionaire Yuri Milner announced Breakthrough Listen, a 10-year, $100 million initiative to conduct the most comprehensive SETI survey in history. Using some of the world's most powerful radio telescopes, including the Green Bank Telescope and the Parkes Observatory in Australia, Breakthrough Listen has been scanning the nearest million stars, the entire galactic plane, and 100 nearby galaxies for signs of technological activity. The project has generated petabytes of data. It has developed new algorithms for identifying artificial signals in a sea of natural noise. And as of the time you're lying in this field, it has found nothing confirmed. But searching is only half of the equation. The other half, the half that makes some scientists break into a cold sweat, is broadcasting. And this is where the debate gets genuinely heated. Remember the Arecibo message from 1974, that deliberate transmission toward a star cluster 25,000 light-years away? That was a symbolic gesture, a postcard flung into an ocean with no expectation of a reply for 50,000 years. But more recently, a movement called METI, Messaging Extraterrestrial Intelligence, as opposed to simply searching, has advocated for actively and repeatedly transmitting signals toward nearby star systems. The organisation, led by the scientist Douglas Verkoch, argues that passive listening has failed for 6 decades, and that it is time to try the other side of the conversation. The opposition has been fierce. In 2015, a group of prominent scientists and thinkers, including Stephen Hawking, Elon Musk, and dozens of others, signed an open statement cautioning against deliberate transmissions without broad international consultation. Their concern was straightforward and echoed the dark forest logic we explored earlier. If you do not know who is listening, shouting might be the last thing you ever do. The astrophysicist David Brin has been particularly vocal, arguing that METI advocates are making a decision on behalf of the entire human species without the consent of the entire human species, which is, at minimum, a bit presumptuous. There is a quirky and somewhat comic dimension to the debate. In 2008, NASA transmitted the Beatles song across the universe toward Polaris, the North Star, to celebrate the agency's 50th anniversary. The transmission will take roughly 430 years to arrive. Whether alien civilizations will appreciate mid-century British pop music is an open question, but the gesture captures something essential about the human impulse to reach out, the stubborn, irrational hope that someone is listening and that they might enjoy the tune. You smile in the dark. The impulse is absurd and beautiful at the same time. A species that has spent the entire night confronting the possibility that the universe is empty, hostile, filtered, simulated, or slowly dying, and its response is to beam a Beatles song into the void. There is something defiant about it, something that refuses to accept the silence as final, but the silence persists, and the question of whether to keep whispering into it or start shouting has no easy answer, because the answer depends on which version of the universe we actually live in. If the zoo hypothesis is correct, shouting does not matter. They already know we are here. If the dark forest is correct, we are already dead and just do not know it yet. If the great filter is behind us, we have nothing to fear. If it is ahead of us, no amount of silence will save us. The telescope keeps listening. The night keeps quiet. And you keep lying in the grass, caught between the impulse to call out and the instinct to hide. The impulse and the instinct circle each other in your mind like two animals unsure whether to fight or lie down together. And slowly, As the night tilts past its deepest point and the faintest suggestion of something, not light, not yet, but the memory of light, touches the far edge of the horizon, you arrive at the place this journey has been leading you all along. You have to make peace with the dark, not because the dark is safe. You have spent hours learning all the reasons it might not be, not because the dark is empty. You have learned that emptiness itself is a kind of structure, an architecture of absence built on invisible scaffolding by forces you cannot see or name, and not because the dark does not matter, it matters immensely. The silence of the cosmos is either the most important warning in the history of intelligence or the most important gift, and you cannot tell which. But you have to make peace with it because you are here. Because whatever the universe is, filtered or forested, simulated or heat-dying, haunted by berserker probes or watched by patient zookeepers, the fact of your existence is not diminished by any of it. You're a thinking thing in a cosmos that, as far as you can confirm, has produced vanishingly few thinking things. You're a brief, warm flicker in an ocean of cold. And the flicker is not less meaningful because the ocean is vast. If anything, the opposite is true. Consider, for a moment, the sheer improbability of you. Not in the abstract, motivational poster sense, but in the concrete, statistical, cosmological sense we have been building all night. The universe had to bang into existence with precisely the right physical constants, the strength of gravity, the mass of the electron, the cosmological constant, tuned to values that allow matter to clump, stars to burn, and chemistry to happen. Physicists call this the fine-tuning problem, and it is staggering. If the strong nuclear force were even 2% weaker, no atoms beyond hydrogen would exist. No carbon, no oxygen, no you. If the cosmological constant was slightly larger, the universe would have expanded too fast for galaxies to form. If it was slightly smaller, the universe would have collapsed back on itself before the first star ignited. The margin is so narrow that some physicists have compared it to balancing a pencil on its tip, not on a table, but on a needle point during an earthquake in the dark. Scholars still argue about what fine-tuning means. Some invoke the anthropic principle, the idea that we can only observe a universe compatible with our existence, so of course the constants look tuned, because we would not be here otherwise. Others suggest a multiverse, an infinite array of universes with different constants, and we happen to be in the one where things worked out. Still others see fine-tuning as evidence of design, though that interpretation raises more questions than it answers. The debate is one of the most profound in modern physics, and it has no resolution in sight. But whatever the explanation, the result is the same. You are here, in a universe that did not have to produce you and almost certainly had better things to do. And then, on top of the cosmic fine-tuning, you needed every single one of those lucky breaks we catalogued tonight. The Theia impact and the Moon, Jupiter's gravitational shield, plate tectonics and the magnetic field, the oxygen catastrophe that was also an oxygen miracle, the 5 mass extinctions that cleared the stage for new acts again and again, the asteroid that killed the dinosaurs and freed the mammals, the strange, unexplained encephalization event that gave primates brains 3 times larger than they should have been, the invention of language, of agriculture, of writing, of telescopes, of radio, of the absurd, defiant impulse to beam a Beatles song at a star 430 light-years away. Every one of those events had to happen in the right order, at the right time, on a planet sitting in the right part of a galaxy, sitting in the right part of a universe running on the right physical constants. Remove any single link and the chain breaks. You're not just unlikely. You're so unlikely that the word unlikely does not have enough letters to carry the weight of what it is trying to say. And this is where the emptiness becomes something other than terrifying. Because if the universe is as empty as it appears, if civilizations are as rare as the silence suggests, then consciousness is not a commodity. It is not a background feature of the cosmos sprinkled everywhere like salt. It is a jewel. It is the rarest thing the universe has ever produced, and you are it. Right now, lying in this field, breathing this air, hearing these crickets, you are the universe experiencing itself. You are the part of the cosmos that learned to ask where everybody went. There is a historical echo here that feels appropriate. In 1990, the Voyager 1 spacecraft, having completed its tour of the outer planets, was commanded to turn its camera back toward Earth from a distance of about 6 billion kilometers. The resulting image, championed by the astronomer Carl Sagan, showed Earth as a tiny speck, a pale blue dot suspended in a beam of sunlight. Sagan wrote that everyone you have ever loved, every human being who ever was, lived out their lives on that mote of dust. The image was not meant to make you feel small, it was meant to make you feel precious. The smallness is the point, the vulnerability is the point. In a universe that is almost entirely void, the places where something exists are not trivial, they are sacred. Not in a religious sense necessarily, but in the deepest, most honest sense of the word, they are set apart, rare, worthy of protection. So here you are. The universe is empty, and it might be empty for a reason. The great filter might be behind you. The dark forest might be real. The grabby aliens might be on their way. The heat death might be inevitable. All of that might be true, and none of it changes the fact that tonight, on this particular planet, in this particular field, a conscious mind looked up at the stars and felt something. Wonder, fear, curiosity, a strange, stubborn hope that the silence is not the end of the story. Maybe the emptiness is not a warning or a gift. Maybe it is a canvas, and maybe the only thing the universe is waiting for is for someone, anyone, to start painting. And now the night softens around you. The tension that has been building in your shoulders for the last hour begins to release, slowly, the way a held breath eventually lets go. The grass beneath you is still cool, still damp, but it feels less like a stage now and more like a bed. The stars above are still vast and still silent, but the silence has shifted. It is no longer the silence of menace or mystery. It is the silence of a room after the conversation has ended and everyone has said what they needed to say. A comfortable silence, the kind you share with someone you trust. Your breathing slows, your eyelids grow heavy, and you let them. The crickets have found a rhythm that matches your pulse, or maybe your pulse has found a rhythm that matches theirs. The faintest breeze moves across the field, carrying the scent of earth and distance, and something you cannot name but have always known. The stars blur slightly, not because they are moving, but because your eyes are closing, and that is fine. That is exactly as it should be. The universe will keep its secrets for one more night. The voids will go on being vast. The dark matter will go on being invisible. The light from distant galaxies will continue its long, lonely journey through the expanding dark, and some of it, a tiny, precious fraction, will land on this field tomorrow night, whether you're here to see it or not. But tonight, you were here, you looked up, you asked the question, and for a few beautiful hours the emptiness was not empty at all. It was full of you. Sleep now. The cosmos will still be there in the morning, and so, remarkably, improbably, wonderfully will you.